Dear students, hope all you are doing very fine. Today, I, Dr. Pushpal Ghosh, Assistant Professor of Dr. Hori Singh Gaur Central University, will deliver a lecture on very important topic, quantum mechanical operators. And the subject expert or content expert of this topic is Dr. Mautusi Manna, Senior Scientist, CSMCRI, Bhavnagar. After this lecture, you will learn that what are the quantum mechanical operators, what are the eigenfunctions, eigenvalues, what are Hermitian operators, and how Schrodinger equation can be formulated as an eigenvalue problem. Now, you know that quantum theory is based on two very important constructs, operators and wave functions. An operator is a symbol that instructs us to do something to whatever follows the symbol. For example, let us consider that dy by dx to be the d by dx operator operating on the function yx. Similarly, let us take square root, which is called at sqrt, integrating operators, partial derivatives, let us say with respect to y, that is dy by dx, are other example of various kinds of operators. So, it is clear that operator and operand, that means the function on which operator acts, must be compatibles. Normally, an operator can be denoted by capital letter with a caret over it, which normally we call a cap. Thus, we can write a cap fx is equal to gx to indicate that the operator a cap operates on fx function to give a new function gx. Now, let us take some examples. For example, a cap 3x, where operator a is equal to d square by dx square. Now, performing this above operation, we can found that a cap 3x is equal to d square by dx square 3x is equal to 0. Similarly, we can take another example, where a cap is equal to d square by dx square plus 2 d by dx plus 5. Now, when we operate on x square, we found that d square by dx square into x square plus 2 d by dx into x square plus 5 into 2. So, altogether you are getting 2 plus 4x plus 5x square. Now, let us understand the sum and difference of two operators, say a cap and e cap, by the equation known as a cap plus e cap fx is equal to a cap fx plus e cap fx. Similarly, when we subtract, then it comes like a cap minus e cap into fx is equal to a cap fx minus e cap fx. For example, if we take c cap equivalent to d by dx, then we can write c cap plus 3 cap into x cube minus 5 equivalent to c cap into x cube minus 5 plus 3 cap into x cube minus 5, which is equal to 3x square plus 3x cube minus 15. So, 3x cube plus 3x square minus 15. Now, we can define the product of two operators a cap and e cap by the equation a cap e cap fx equivalent to operator a cap into operator e cap into fx. So, we first operate on fx with the operator on the right of the operator product, and then we take the resulting function and operate on it with the operator on the left of the operator product. For example, 3 cap c cap fx is equal to operator 3 into c cap fx is equal to 3 cap f prime x is equal to 3 f prime x. For this example, there is no difference in the final result whether we first applied one operator or the other, but not always a cap e cap and e cap a cap have the same effect. To understand this, we have to take another example with operator c cap and x cap, where c cap is equal to d by dx. Now, if we write c cap x cap fx is equal to d by dx x fx is equal to fx plus x f prime x is equal to 1 cap plus x cap c cap into f x. Now, if we write x cap c cap f x is equal to x cap into d by dx f x is equal to x f prime x. Thus, we found that operator a cap e cap and e cap a cap have the different effect here. A major difference between operator algebra and ordinary algebra is that numbers of the commutative law of multiplication, but operators do not necessarily do so. Now, we know AE is equal to A if A and E are numbers, but operator A cap E cap and operator E cap A cap are not necessarily equal operators. Now, A cap E cap and E cap A cap are the same, then the operators A cap and operators E are said to commute with each other. Now, the commutator of the two operators A cap and E cap is defined as A cap comma E cap is equal to third bracket A cap E cap minus E cap A cap. Now, if A cap E cap with the function of f x is 0 for all f x on which the commutator acts, then we write that operator A cap and E cap is equal to 0, and we say that A cap and E cap commute with each other. We have to understand this thing very nicely. Let us evaluate the commutator of A cap E cap when A cap is equal to d by dx and E cap is equal to x square. Now, let us consider that both these operators act upon an arbitrary function f x. So, we can write A cap E cap f x is equal to d by dx x square f x. Now, upon differentiation we can find 2 into f x plus x square into d by dx. Now, E cap A cap f x is equal to x square into d by dx f x. By subtracting these two results, we obtain third bracket A cap E cap minus E cap A cap into f x is equal to 2x f x. Now, I will discuss linear operator, which is very important. In quantum mechanics, the operators which are used are all linear operators. An operator A cap is said to be linear if the following condition holds, like A cap third bracket C1 F1 x plus C2 F2 x is equal to C1 operator A cap F1 x plus C2 operator A cap F2 x, where C1 and C2 are constants and F1 and F2 are the two functions. For example, the two operators differentiate and integrates are linear because if we operate d by dx on C1 F1 x plus C2 F2 x, we found C1 df1 by dx plus C2 df2 by dx. Similarly, C1 F1 x plus C2 F2 x dx is equal to C1 F1 x dx plus C2 F2 x dx. On the other hand, square operator, which is normally called a square SQR, is non-linear, because if we operate square on C1 F1 x plus C2 F2 x, we found C1 square F1 square x plus C2 square F2 square x plus 2 C1 C2 F1 x F2 x, which is not equal to C1 F1 square x plus C2 F2 square x. Hence, it is proved that square is a non-linear operator. Similarly, it can be proved that square root, which is termed as SQRT, is also a non-linear operator. Let us say A cap f x is equal to square root of f x. Now, on putting, we found that A cap C1 F1 x plus C2 F2 x is equal to C1 F1 x plus C2 F2 x to the power half. So, which is essentially not is equal to C1 F1 to the power half x plus C2 F2 to the power half x. So, we can say that square root also a non-linear operator. It sometimes happens that function f x, when operated by operator A, produces the same function and multiplied by a constant A. Then we can write that operator A f x is equal to small a into f x. Now, this equation is called an eigenvalue equation, which is very important in quantum mechanics. The function is said to be an eigenfunction of the operator A cap, and small a is called the corresponding eigenvalue. Eigen is a German word meaning characteristics, Eigenvalue is a hybrid word. Basically, it means, or this meaning may be characteristics weird. Now, let us solve a very simple problem. Problem is that we have to show that e to the power alpha x is an eigenfunction of the operator dn by dx. That means, differentiate with respect to x for n times. Now, question is what is the eigenvalue? We have to calculate it. Now, if we differentiate e to the power alpha x n times and obtain dn by dx, e to the power alpha x is equal to alpha to the power n e to the power alpha x, and so we can say the eigenvalue is alpha to the power n. Now, the operators can be imaginary or complex quantities. We can see that the x component of the momentum can be represented in quantum mechanics by an operator of the form operator p x, which is equal to minus I h cross del by dx. Now, again we can solve another problem. The problem is that we have to show that e to the power I k x is an eigenfunction of the momentum operator, where operator p x is equal to minus I h cross del by dx. Also, we have to find the eigenvalue. Now, again if we apply the momentum operator, that means operator p x to e to the power I k x, and find operator p x e to the power I k x is equal to minus I h cross del by dx e to the power I k x, which is equal to h cross k into e to the power I k x. So, we can see that e to the power I k x is an eigenfunction and h cross k is an eigenvalue for the momentum operator. Now, as a home task, you can check whether the following eigenvalue equation or not. That means, which I am writing here, whether these are following the eigenvalue equation or not. Number 1 is d by dx e to the power I k x. Number 2, you can solve whether h cross by 2, h by 2 pi I del by dx into e to the power I k x. A third problem, you can solve it del square by dx square cos omega x. Now, I will explain another very important topic, which is Hermitian operator. In quantum mechanics, the wave functions which are allowed are always chosen from the class of functions which are single valued and continuous. Only exception is that except at a finite number of points where the function may become infinite. So, in the complete range of variables, you can get the value of psi, and which give a finite result when the squares of their absolute values are integrated over a complete range of variables. So, this is very common functions of the wave functions. Now, we are considering psi and phi are two functions of the above class. Now, if operator A can be such that integration over space phi star a cap psi d tau is equal to space integration psi a cap star phi star d tau, then the operator a cap is said to be an Hermitian operator. That means, if any operator following the above condition which I have just said, we can call it as a Hermitian operator. Now, it can be proved that eigenvalues of the Hermitian operator are real. This is also very important. Now, the question is how we can prove it. Now, let us take psi v n eigenfunction of the Hermitian operator a cap with the eigenvalue a, small a. Now, we can write that small a cap is equal to small a cap psi is equal to a psi, which we can give equation number 1. Now, taking the complex conjugate of it, we can found a cap star psi star is equal to a star psi star, which is equation 2. Now, multiplying left of equation 1 by psi star and integrating over space, we can get psi star a cap psi d tau is equal to small a into psi star psi d tau, which is labeled as equation 3. Now, by multiplying left of equation 2 by psi and integrating over space, we can get integration psi a cap star psi star d tau is equal to a star integration psi star psi d tau, which is labeled as equation 4. Now, as we learnt already that if the operator is Hermitian, then we can equate this equation 3 and 4. Okay. So, the left hand side of the equation 3 and 4 will be equal. So, we can write that psi star integration psi star psi d tau is equal to a star into psi star psi d tau. So, we can write that a minus a star into integration psi star psi d tau is equal to 0. Now, psi star psi d tau will be not equal to 0. So, we can write a minus a star is equal to 0. So, a is equal to a star. That means that we can say, or it can be said, that the eigenvalues of Hermitian operators are real. Now, I will explain one very important topic of the Schrodinger equation. So far, I have taught you about the spectroscopy, and now my subject is to connect between the quantum mechanics, which can be done by Schrodinger equation, which is equation for the wave function of a particle. This equation can be regarded as fundamental axiom of quantum mechanics, as Newton's law is fundamental postulate of classical mechanics. So, this equation can be regarded as fundamental axiom of quantum mechanics, as Newton's law is fundamental postulate of the classical mechanics. Though we cannot derive Schrodinger equation at this moment, but definitely we can trace Schrodinger's original line of thought. We can hypothesize that if matter possesses wave-like properties, then there must be some wave equation that will govern them. The classical wave equation can be written as del square u by del x square is equal to 1 by v square del square u by del t square, where u is the displacement of the string, which is called a standing wave, and is the function of two independent variables x and t. Now, the equation 5, which I just mentioned, can be solved by the method of variable separation technique, and u x t can be written as the product of a function of x and harmonic or sinusoidal function of time. Now, we can write u x t is equal to psi x cos omega t, which is labeled as equation 6. Because psi x is the spatial factor of amplitude of the mu u x t, and we shall call psi x the spatial amplitude of the wave. Now, on substituting equation 6 into equation 5, we can write del square psi by dx square plus omega square by v square psi x is equal to 0, which is labeled as equation 7. Now, we can introduce the idea of de Broglie matter waves, which I just mentioned 2 classes back, into equation 7. The total energy of a particle is the sum of kinetic energy and potential energy. We can write E is equal to p square by 2m plus ux, where ux is the potential energy. Now, the equation 8, which I just mentioned, can be rearranged as p is equal to second bracket 2m e minus ux to the power half. Now, according to the de Broglie equation, we can write lambda is equal to h by p. So, by putting p, we can write h by 2m e minus ux to the power half, which is labeled as equation 10. Now, the factor omega square by v square in equation 7 can be written in terms of lambda, because we know w is equal to 2 pi nu and nu lambda is equal to v. So, putting all together, we can write omega square by v square is equal to 4 pi square nu square by v square is equal to 4 pi square by lambda square. Now, putting the value of lambda, it will be 2m into e minus ux divided by h cross square. Now, substituting into equation 7, we can write d square psi by dx square plus 2m by h cross square into e minus ux psi x is equal to 0. Now, this equation is known as very famous time independent Schrodinger equation. Importantly, this is a second order differential equation for psi x and for a particle of mass m moving in a potential field described by capital Ux. The psi x is a measure of the amplitude of the matter wave and is called the stationary state wave function of the particle. Now, the equation 11 can be rewritten as minus h cross by 2m into del square psi by dx square, plus capital U x plus psi x is equal to E psi x, which can be labeled as equation 12. Now, I will explain very important thing, that how Schrodinger equation can be evaluated or can be formulated as eigenvalue problem. Now, the left hand equation of the equation 12 can be formulated as minus h square by 2 m into del square by dx square plus capital U x psi x is equal to E psi x. Now, we can relate the operators in brackets by h cap, and equation 13, which I just mentioned, can written as h cap psi is equal to E psi x, which is equation. Now, the equation 14 shows that Schrodinger equation can be formulated as an eigenvalue problem, and the operator h cap is called the Hamiltonian operator. The wave function is an eigenfunction, and the energy is an eigenvalue of the Hamiltonian operator. Also, this shows a correlation between the Hamiltonian operator and energy. Like the final form will be h cap is equal to minus h cross by 2 m into del square by dx square plus u x, which is labeled as the equation 15. Now, I can summarize my talk today. So, in this module we have learned an operator is a symbol that instructs us to do something to whatever follows the symbol. We have learned about various aspects of operator algebra, like how two operators will commute with each other, conditions of an operator for being linear operator, etc. We have discussed eigenvalue, eigenfunction and eigen equation by taking various examples. The condition of an operator for being Hermitian is being discussed. In addition, we have proved that the eigenvalues of an Hermitian operator are real. We have explained the condition of an operator for being Hermitian. In addition, it is proved that the eigenvalues of Hermitian operators are real. Most importantly, we explained Schrodinger equation from classical wave equation. Then we have shown that how Schrodinger equation can be formulated as an eigenvalue problem. Lastly, we have shown a correlation between the Hamiltonian operator and energy. Thank you very much for your kind attention.